Okay. Well, thank you for coming, and I'm sorry we're starting 5 minutes late. I think we'll still be in a good queue here. Today's session that I have locked in is Alaskan Emerging Energy Applications. So what I like to do sometimes is take different projects that are happening on the university where they're doing planning or assessments for particular non-conventional types of energies and just let the public know what's happening and let them know that there is different styles of research that's ongoing in trying to determine, especially for a lot of the rural areas, whether there's a more cost-effective way or a supplementary way of providing power, which would be electricity or heat, to other locations in the state. So all of the you're all about to see is kind of in the research stage, but it's something that often gets people to think about possibilities that might be applicable in their area. Most of the studies I've grabbed from the Alaska Center for Energy and Power, who we work very closely with, in addition to the Northern Engineering program here on campus. So if you have any questions, because I'm not doing the actual research, I'll try to field as many as I can, and then I'll try to pitch it on over to you, over to the person if I've got your contact information who knows more about the particular technology or the type of planning or the type of assessment that they're using. So the first slide, I've just got the actual locations of the energies that we'll look at. Obviously, there's Anchorage and Fairbanks along the rail belt. And just south of Anchorage is Nenana, where we'll take a look at a hydrokinetics research project. Minto, where we'll take a look at methane from thermokarst lakes that are starting to melt and change on the landscape. And in Tanana, we'll take a look at biomass, that is cordwood applications, by utilizing driftwood that they're taking advantage of. And I think I have a picture in here also of Ruby of an in-river generator in the Yukon River. And then finally, it won't be quite in this order, so keep your eyes out as far as the order that we go through them. But Pilgrim Hot Springs, all the way to the west, we'll take a look at some geothermal that's being done on an old abandoned church orphanage site near the Nome area. Now, in this case, you'll notice that most of the research that's being done is pretty much on the same, almost the same latitudinal line. And I guess the commonality that might tie them together is, other than Minto, is well, even Minto with the thawing out lakes is water. So Nenana is on the Tanana, Minto is on the Tanana, and Tanana is at the headwaters where the Yukon, which is the blue line running through the word Tanana, and the Tanana River from Minto collide. And then Ruby is on the Yukon. And then we also have Pilgrim Hot Springs, which is out in Norton Sound. And there's real no plan or purpose to these having been picked as research projects in one big large group, because we were analyzing the interior waterways of Alaska or anything like that. Different I guess, reasons came about to go ahead and take a look at these projects. So the first one that I'll show you is actually one that I'm going to show a lot of images, a lot of different types of technology I'll mention that are being used to see through radar, through satellite, and through plane photography, aerial photography, what the chances are of making these economically viable projects. The first one is in Tanana itself, which is about 60 miles west. Fairbanks, as I mentioned, it's at the confluence of the Tanana and Yukon River. And you have kind of a picture there after they come together. That island in the middle is called Long Island, excuse me. And then just above that to the north is the small, tiny grid of Tanana. The white strip, the white horizontal strip that's perfectly straight is their airfield. So you're talking of a community that's less than 500 people, yet has been there for a good amount of time and has taken some real advantages of their location. So when fuel oil was getting a few years ago up to be about $6 a gallon, to put on a barge at Nenana, drive a truck down to Nenana, put it on a barge, and then ship it over to Tanana, 60 miles or so west. The tribal or the city planner, I guess, or administrator, had gotten the idea that they probably needed to get back, just due to cost, to kind of a traditional wood hauling economy. And so he started out small by working with a grant, and he was a real go-getter as far as grants that would allow them to go ahead and find a common community building in which they could go ahead and figure out a way of reducing the energy load. And that building for Tanana was the washateria. It's where people took showers, washed their clothes, and there was an immense amount of heating that went on at 60 below, as well as obviously during the other seasons, that took a lot of BTUs to go ahead and keep the washateria open and running. So the administrator went ahead and started with 2 EconoLine, or EcoBurn rather, boilers, which are a type of boiler where you can put in small loads of stick cordwood. And they started with that, and they saved a whole lot of money. At $6 for what traditionally would be the BTUs that you would get out of cordwood, let's say at $250 a cord, okay, which isn't unreasonable in Fairbanks right now. In fact, it's probably a little bit lean on the good deal side. But if you compare that with $4 a gallon fuel oil, you get twice as many BTUs from the wood per dollar, assuming that the wood is 18% or less moisture, because it takes more BTUs out of the equation, and costs you more to, I guess, vaporize the water in the wood. But if it's less than 18% moisture, you can get twice as many BTUs as far as the bang for your buck at $4. Well, Tanana was looking at $6 a gallon fuel oil. So they were looking at a savings of, due to fuel oil being even 30% more expensive than that. So they, as you can see from the topographical map, there's a lot of valleys that come down to the main river, to the Yukon. But as you can tell from the screenshot that has the aerial photograph, there's a lot of green to that, and a lot of that is good spruce timber, tall spruce, generally speaking. And so there's a mix of birch and aspen. The idea was they could go ahead and cut down the spruce. They didn't know how cost effective it was due to the price, obviously, of diesel being high, also gasoline for snow machine and four-wheeler. How far back, they didn't know. Could we go back into the woods, drag it out, and still be beating fuel oil? The other component was, though, that in the springtime, when the ice would break up on the river, due to the erosion under the banks of the river on the Tanana and on the Yukon, you'll often see trees that are leaning in at 30, 45, 60 degrees. The soil under them is being undermined by freezing and thawing and breakup, and it cuts the riverbank, and those trees fall in the river. And what they were finding was that by the time the trees came downriver, large, tall spruce trees and birch from the banks along the Tanana and the Yukon, they were already cut and cleaned. In other words, they'd been dumped in, and they still had the root system, so that would have to be chopped off. But for the most part, they were delimbed. The ice and the jostling about on the rocks and the rivers broke off all the limbs, and it also debarked. so that you had maybe a 30-foot stick of tree that all you needed to do was cap off the end as far as roots and let it dry on shore, because it's just floating by down the river going out to the Pacific Ocean. If you can capture it and put it on shore, the wood was a little sandy, so there was concern of burning it, and that if you burned it hot and fast, that you would end up with kind of clunkers, almost like a rude glass that would form from all the sand and the silt in the wood. But they haven't found that to really be so much a problem as they had anticipated. The other thing that they would find is that when they pulled it up on shore, it didn't really take that long in the dry interior here to dry out that wood, even though it had been bobbing in the river. So at first, they had decided to go ahead and inventory, well, at least on the land, what kind of wood do we have? And then where would it be worth going for on the land? There is work in getting it out of the river. Yes, it is debarked and the limbs are off for the most part, but it can be somewhat dangerous work. You have to get your boat out there with your a large horsepower motor, and you basically have to lasso these logs as they're floating by and pull them in and drag them up on the shore. So for some, the thought was you can use that fuel source, but you also need to be cognizant that felling trees is pretty straightforward if there's enough trees of the right kind. So they went ahead and they actually had guys go out who are foresters and do inventories, and then they color-coded these GIS maps, Geographical Information Systems. That stands for Computerized Map. And they had an idea then of which wood was, growing in which area that they could hopefully take advantage of. They also then, it was pretty easy from there to determine by doing kind of a thickness inventory of each acre, where you wouldn't get any kind of woody growth, which obviously is the gray, which is the river. They weren't considering the driftwood. They were just saying growth. The sites that were low as far as the density, which are the orange areas, the medium sites being green, and then the high density areas of wood, which is not surprising, are right along the river because trees grow well when there's water nearby, right? So they then went ahead and they had to decide, which land was viable due to the fact that it was native land, or it was allotment just to the tribe of Tanana, or it was BLM land. And they also needed to make a map then of these regional, I guess you would call them management units, which each have a management plan to try to make sure that the habitat is protected, keeping in mind the animals of that particular region and such. Now these regions go way out into the white area, but they kind of cookie cuttered it against this phase 2 project extent, because that's as far as the area they wanted to study. So the nice thing about GIS maps is that you can have all these regions and such, but you can kind of cookie cutter with your own outline where you want to study. And then they put in the roads, because obviously you're going to have to drive pickups, snow machines, or four-wheelers to drag these logs in that you cut down. And what they basically came up with then, by kind of layering a lot of these maps on top of each other that were done by footwork, by foresters going out, and some of these were done by using flyover data. That aerial photography has been used for years in forestry as far as detecting density and such, looking at the photos under magnifying glass, and then really getting an idea of where the boundaries are of the heavy, dense areas, the wet areas and such. And what they determined was that here's town right here, but there were some areas close by that had 30 to 50 acres a ton. So it was worth thinking about maybe thinning those, maybe not clear cutting, but thinning those out because they were fairly close by. But you also have some dense areas here on the other side of the river, and on Tanana side of the river. So the question then became, for those areas, besides what was close to get to the high density areas in the hills here, how far would you have to drive with that overlay of the roads that they had, of what was possible? And then from figuring out how far it was to drive, the cost of fuel, how much time it took, they were able to come up with kind of a guesstimation of what the cost would be. And obviously, the $30 a ton or less, the really cheap stuff, is really close by, right? And that's taking into account the density and everything like that. So this was actually going to be a pretty good area. Out in these areas, there might be road, but it really wasn't worth it just because you were at $150 a ton to bring it in. So Tanana, in general, used this type of technology to instruct their people of where to go. Now, to do the logging, in the end, they are also going to do some studies, and this is that island right across the way. They're able to, with a GIS map and detecting the terrain, the wet areas and such of just that island, put X's where they want to plant or they want to go ahead and thin. But they're going to go ahead and study plots in the areas where the X's are to see what growth is for the next 10, 20 years. Now, uniquely for Tanana, because it had all that wood coming down, they were able to switch over to a wood economy in a kind of cultural way. When I used to go through the areas as a social services worker with Tanana chiefs, a lot of the elders would complain that the young folk were doing their Nintendos or were, doing different things at school, but they weren't learning the practical things like trapping and collecting wood, things that kept them healthy as well as required skill. And the city administrator in this case said, you know what, we're going to get more boilers on more grants. And indeed they did. They have 11 boilers for their town. Their senior citizen center or assisted living, their washateria, some of the new school housing that they've been building, super efficient housing for teachers because it's not really an open market there for housing. So they supply that. And some of their other buildings like their firehouse and such, they decided to go to wood because of this vast savings that they could have. And in doing so, they went ahead and said, we're going to set a price as a city at $250 a cord. You bring in a cord, we don't care whether it's out of the river or it's out of the hills. It needs to be a true cord, but we'll pay you $250. So people who didn't have jobs before, at their own will, were going out whenever they wanted to and bringing in wood, and the city coffers would pay for it and use that as fuel for its different functions. And in this case, $250 a cord was unsplit, but they had boxes to make sure it was true. And a lot of the guys who didn't have saws to begin with, almost like the old company store towns in the West with mining towns, they would the city bought chainsaws and bought different equipment and said, look, here's the deal. We'll sell you a chainsaw and we'll give it to you now, and then you pay it off in payments off each time you bring in a cord for the first 10 cords. And so if the chainsaw was $200, they'd take like $20 off the money that they gave them for the first 10 cords, and then the chainsaw was free. And so there's been kind of this economy that's boomed that wasn't there before, to the extent that other villages have heard about it. And Stevens Village upriver put together went and cut their own timber around that village area and put together a huge raft of over 80 cords of wood. It was 6 foot deep in the water, I'm told. Kind of like the old Tom Sawyer days. They would just, in the old logging days in the Midwest, they would just lasso it up. And they rode for 3 days, I think, down camping out, the Stevens villagers, and pulled it into Tanana, got it pulled up on the beach with heavy equipment, and sold 80 cords all at once in one bang. So this is an example where implementing a smart, thought-out energy system can actually help economically for the region. Now, over in Norton Sound by Nome, there's an old Catholic orphanage, I believe it is, called Pilgrim Hot Springs. And it's up against the mountain hills, between the mountain hills and then the actual coast. I think they drive in about a half an hour. And it's been suspected for some time that, they've had natural pools and such of water, that there might be some energy that could be extracted from hot water under the ground if they could go ahead and tap a well casing all the way down, get that hot water to come up and maybe spin a turbine, a small turbine, and create electricity. And this has been done in other areas. These are kind of like micro geothermal projects. In Iceland and other areas, they have massive industrial-sized geothermal projects that they work with and trying to tap the hot water. But in this case, again, we're talking about well casings. But well casings can be expensive, and it's hard to know how far down you're going to actually encounter the water. And there are certain parameters that have to be there with the heat of the water and the distance for it to travel up, from what I understand, and I'm being very general about this. You can read more about it on Alaska Center for Energy and Power's website in order to capture the heat. So they went ahead, and they are led by the gal who up here at Chena Hot Springs incorporated a Rankine cycle engine or generator, which was a way of recouping from a heat difference of 140 degrees, which is not very hot water coming out of the ground, with a more cold water. The difference of temperature they were able to extract in such a way with these Rankine cycle engines, and they were able to produce actual electricity that they then, in heat, that they then port to different parts, and even have a growing operation in the winter, a very large one that they use the heat for in Fairbanks, or out at Chena Hot Springs. And so Gwen, who was the head of that project at one time, has kind of made this a milestone, or not a milestone, but kind of a prime project for Alaska Center for Energy and Power. Now the question is, how do you detect from overhead where you ought to drill? Because these drills are very expensive to bring in. Well casing can be expensive. So what they decided to do was, here's an overhead map that was done by satellite. In the black area is kind of a staging area, and you can see some pools that are up in here, and some naturally occurring pools. And then you have the buildings, which are right here, the barn and other areas that were part of the orphanage. So what they used was a technology called FLIR, which is forward-looking infrared. It's not much different than the type that energy raters use when they point a thermal gun at your house. It's a fairly advanced type of application here, because you're doing it from satellite. And so when they would use this forward-looking infrared from satellite, I believe this was satellite, not airplane, they would be able to see from above where the hottest spots were. And they're able to determine depth somewhat too, I believe, from these digital imaging models once they get them into a decent software program. So they're able to take a look at those areas that maybe weren't the best to drill in, maybe some of the cooler compared to the hotter places, and kind of knew in a kind of a scouting technique where to start drilling to try to hit that water for the temperature areas they wanted. Next, any questions so far on the biomass or on the geothermal? or the communities that they're in? Okay. I should add that Nome, that the Pilgrim Hot Springs is kind of encouraging because some people, do mining up in that area beyond in the hills, and some people, I think, would like to be out of town a ways, but the power lines don't go out that far. In Nome, the power lines, for the most part, most of the power is brought in by running diesel generators, and you probably read the story a couple of years ago where they weren't able, because of storms, I think, to get the barge with the city's fuel oil up before an early cold snap, and then they were stuck in the winter without fuel oil, and they had to have a Russian ice cutter, and Vitus Marine helped out with some of the logistics and basically cut the ice to get a diesel ship in the middle of winter within, I think, 2 miles of the tanks. Then they had to run hose all the way to the tanks and fill them up with millions of dollars worth of diesel. And so Nome has tried to figure out other ways. It's fairly windy there. They have a couple wind turbines, but they're a community who, again, similar to Tanana, is not on the road system and doesn't have the luxury of just going up or down the road if there's difficulty with their energy source. Nenana is a little different. Nenana is on the Parks Highway, 60 miles south of Fairbanks. And the project here is taking a look at a very slow meandering river with a lot of sandbars and a lot of debris, these large trees coming down. How can they set up an in-water turbine with a cable coming off it to bring electrons back onto shore from electricity being generated right in the river? The biggest difficulty that they have, though, is debris smashing up the turbine. So they used sonar, underwater sonar. And what they wanted to determine was, when you're investing quite a bit of money in a device, how do you find pockets of water that are fairly deep where you can extract a lot of energy and avoid, if possible, debris from banging into your machine? So in this case, you'll see this stretch of Nenana River, they went ahead with sonar and shot line sights across various places where you'll see those white lines that correspond with the fluorescent green lines. And that was to see what the depth was, but they also need to know flow, how fast it's going. And so the darkness of the map itself in that channel shows the depth, and then the the kind of horizontal or the vertical little rainbows here that are coming off the transit or the line that's shot across here, those would have to do a speed. And so you can take a look and see, where should I put my in-water turbine? Well, this area seems pretty good because it's nice and deep, and it looks like there's somewhat decent of a flow. Here you've got a really good flow, and it's really deep. Now, this picture, underwater sonar picture, doesn't tell the whole story, though. No. Because another problem is turbidity. If it's very rough through here, that may not do well. But this is a tool that they're using to determine for the Nenana River where should they set the turbine. And here's just a cross-sectional view of just looking strictly at the depth in the flow. And this is a device that was put in Ruby to try to, on the Yukon, try to also extract in-river turbine energy. Unfortunately, I think the cost came out like at $100 a kilowatt hour or something really crazy, because they just weren't able to get it in a good spot and get it to spin enough, because it costs money to get it out there, to operate it, to detangle it when stuff bangs up into it, and I think debris was a problem. So different places on the rivers, they're trying that. And in Ruby, I believe this is Ruby, you've got kind of a cross-section here where they use underwater sonar to kind of look at the topography and kind of draw the topography in and color code it, again using GIS applications. And so you can kind of see there when they take this ribbon and they kind of interpose it with a satellite photo, you can see where you might place it according to some of the landmarks against the actual bank. Now, the last project I'd like to talk about is out of the School of Engineering, and though the primary purpose of this was not to really look at a commercial source of energy, there's a lot of questions over how the climate change that Alaska is definitely experiencing in various areas might be capitalized upon to go ahead and come up with some cheap energy sources. And so Katie Walters and a group who work out of the Institute of Northern Engineering are here in a picture in a lake right behind the university parking lot, up about a half a mile. And they have found pockets of methane, and they take the college students out there and they have a little lighter and they light the methane when someone bashes the thin layer of ice with a chisel, and then they light it on fire just for kicks, you know. But in this case, they're also trying to demonstrate that there's a large amount of fossil fuel, in this case methane, that is captured in the ground. So you have throughout Alaska, if you've ever done flying, especially in the interior where you have shrub areas where there's maybe not a whole lot of tree cover, you have these pothole lakes, a lot of people call them. And a lot of them, if you were to go down to those lakes, they might be a little spongy on top, but not far beneath. The soil would be frozen hard. It would be permafrost, and they call them thermokarst lakes. And so those lakes have been frozen hard as a rock, at least in the soils underneath the water, for some time. And yet there's been microorganism decay and such going on from some of the brush matter and maybe some of the trees. These are black spruce behind that have fallen in and rotted. And they get caught, the methane gets kind of trapped in, so to speak, by this permafrost. So you've got these pockets in icy soil of gas from decaying matter. And you know, the same thing happens in the lower 48 on a much quicker basis with landfills. They'll put a bunch of garbage in the landfill, food items and clothing and debris, and then they'll often go ahead and scrape a bunch of dirt and plow it over and kind of start fresh, and they're making over time a huge mountain of garbage. But over time, that mountain actually settles. They'll punch down wells and different monitors, and that ground settles because as that garbage under there decays, obviously not the plastics, but the other things that are in there, it decays and you come up with muck and humus, dirt. It's giving off methane often. And so there are landfills in the lower 48 that have taken with landfill refuse, and they've plowed down well casing with a capturing device, and they basically are mining the methane out that's gotten trapped underneath of layers of dirt that are put on with this rotting garbage. Well, and in some cases they've even put subdivisions on them, believe it or not. But there's obviously some engineering challenges because you need to wait till that collapses and settles so you don't have foundation problems. But anyway, that's just a side note. So in a lot of Alaska, if you take a look here at this polar extent using GIS, they're showing here that a lot of Alaska is heated up in general over the last 3 decades. So they took temperatures from various areas and they said, you know, here it was 0 to 3 degrees difference, all right? And in some areas where there was land mass, there was obviously no difference in temperature. But as you got close to the pole here, and we're right here, you had a bunch of spots that were like, I'm sorry, I apologize, this isn't, let me back up. This isn't temperature differential here. This is a change in how long the snow will stay, And so where it's dark red, it's saying that it's 12 days shorter of snow actually staying there. And they also do tests. They've been doing tests in the tundra and the different west, southwest, and northwestern parts of Alaska of measuring the amount of temperature days that the land has been frozen. Now with these thermokarst lakes, you have them frozen for a large amount of times, trapping the methane. They start to thaw out as there's less snow cover. And so as they thaw out, then these bubbles that were trapped, when the soil underneath slowly thaws, it releases the gases. But the gases often come up in a bubble, in a large bubble, and depending on when freeze-up happened, they can get trapped under the lake in the water column, so to speak, freed from the dirt, but now they're trapped in a frozen chunk of ice, depending on how far that goes down, if the ice goes all the way down to the bottom or not. And so you got these pockets. So what they've been doing at INE, and I'm probably lambasting and not doing a very good verbal description, but what they're doing is they're using LiDAR imagery from above. They're kind of shooting kind of arrow vectors down from satellite to test for that vector, that straight shot down to the earth, how dense and thus how deep do you have the ice. And in this case, what they've done then is they've shot one vector right next to each other, right next to each other, right next to each other, and they can almost come up with a depth topography by getting this information back. And you end up with all these little thermokarst lakes that I mentioned. Now, this is over on the Seward Peninsula, northern Seward Peninsula. And so you have a lot of newly formed ice coming in here from the north and the east. And the land, by the way, are the black areas. And the thermokarst lakes, which I mentioned, that are frozen, they're at the permafrost. They're these dark blue areas here. And the data, or the SAR imagery, is used to try to evaluate from the brightness, again, that depth, that amount of ice cover. And so it's kind of a reflective imaging from the way I understand it. So what they're starting to do is they're starting to measure by doing flybys or flyovers how large these lakes are getting. Because over time, as more thaws out, they get larger and larger. And how deep. And they can make sample estimations then on how much of the gases are coming up, and they can infer. And so in Minto, there's been a desire to go ahead and capitalize on this and set up some type of, because they have a lot of flats, and they're about 120 miles, I think, as the crow flies, northwest of Fairbanks, west and maybe a little north, and they have a road system, much like Nenana does. And so they would like to figure out how to get some trucks back in there and some different equipment and to capture that methane rather than just having it go burned up into the atmosphere. So those are 4 illustrations. Some are obviously fossil fuel, like this methane instance where different types of equipment and research methods are being used to try to figure out some emerging technologies that we can extract some type of emerging energies from that we normally don't use. Any questions about the biomass or the geothermal or the in-water hydro or the in-river hydro or the methane thermokarst lakes?
I don't have a question about any of those.
Okay.
The question is, the topic of discussion that we were given was small-scale hydro, and that's what we thought we were coming here to listen to, a lecture on small-scale hydro. So I was just wondering how that got switched around.
Well, on the sheet that I looked at this morning, and I apologize if I misread it, I thought the 21st was emerging energies. But you know what? We've got 15 minutes, and I can certainly show you small-scale hydro. How's that?
Well,
so,
it was a very interesting discussion, and
yeah.
Sure, go for it.
Okay, so I apologize on that.
And well, it might not have been your fault. We might have just put the wrong thing on the poster.
Or I may have misread this morning. I was at my secretary's desk, and I looked, and I said, oh, it's emerging energies. So.
Art, we did have emerging energies as the topic on the OWL calendar, just so you know.
Okay, no problem. Well, let's go ahead and hit some small-scale hydro. How's that? In fact, I'm going to take you on a spin of a portion of a presentation that I did about a month ago called Remote Energy. In other words, how can you get energy from areas that are off the grid? And let me see here if I can bring that up real quick. Are you able to see right now my search box at all?
No.
No, okay. And even when you were speaking and using your cursor or pointer, yep. We never could see that, what you were pointing to.
Okay.
So I don't know if that's a big deal, but
yeah. Well, let's try to get this on real quick, and I will try to in the next 12 minutes then give you a little taste of some hydro.
And I can extend your conference as long as you need it, Art.
Yeah, like another 10, 15 minutes would be nice. Thank you.
Sure.
Okay.
Oh, great. Thanks.
Yeah, so I'll take you on what I have. Let's see. Okay, let's see if this is it. Okay, so I'm going to give you a little background out of my remote energy workshop to get you to the hydro. And I'm going to first of all, though, make sure that I have the option of sharing this. So let's see here. Okay, good. Okay, so tell me if you see right now a PowerPoint show come up that has, I guess, kind of two screens that look the same.
Yes. Practical Alaskan grown remote energy solutions.
Yeah. Were any of you in either of the rooms here for that when I showed it about a month ago or so? Okay.
No.
Well, we've got a little time, and you might kind of get a partial 2-for-1. So let me extend this up so we can get this as large as possible. So I was out in Nome, and I wanted to do a presentation with one of the tribal entities out there, and they said, well, what people really want to know about is going out mining or in the summer how they can get some energy, or they want to know when they go to fish camp for 2 months and are on the river. Some of this is obviously Nome's Eskimo community. We want to know when we go out hunting and stuff, how we can get some remote energy. So let me, I'm going to just try something. Right now you can see the Practical Alaskan grown remote energy solutions. I'm going to see, is it can you see it right now?
The screen hasn't changed. It still says practical Alaskan grown remote energy solutions. And
Okay, and it hasn't gotten any larger or any smaller?
Well, it fills your box.
yeah, it pretty much fills this, you know, the
Good
picture of
deal.
your laptop.
Your screenshot box.
Excellent. Okay, this is the full slide mode that we've tried for a couple of weeks, so this is a good thing. Without running you through the whole presentation, I'll just kind of wet your whistle and let you know what we usually go through, and then I'll get down to the small technologies of making your own energy. So to begin with, obviously there are many remote communities that are off the grid and have stranded energy systems, even for the community. You know, they burn diesel at 30% efficiency, if that, to convert oil BTUs into electricity kilowatts. And their little grid doesn't touch, you know, another grid. They're just kind of standalones. So for years, obviously, there have been, wood has been a way of cooking and preserving food along the river during summer fish camp. And obviously fuels have been used as of late to get around, to get to the game, and also to drag in different types of wood and such. This is, by the way, Venetai, where the fuel in those upper right-hand corner gas cans costs $8.50 a gallon. And so they keep their dogs going for different purposes. And obviously, larger mining operations often are near water, especially if they've got sluice box operations and such like that, maybe on the river. But in general, what I normally do with this workshop is I get people to think about, take a typical week. Last time they were in the woods, maybe it's an annual time they go with the kids once a year they've done for 30 years, as to what do they use energy for, whether it's heat or for electricity, and then what types of fuels do they use. And then I ask them, you know, to estimate the amount of hours for devices that they use, whether it's the little Coleman 2-burner green suitcase stoves, or whether it's LED lights, whatever the case is. And then also what I want them to do, though, is take a look at, as they think on how to become more efficient at their camp off-grid, I want them to, so for instance, changing LED bulbs out for the normal incandescent bulbs, you can use like 1/8 of the electricity. Well, if you're generating electricity off of some device, renewable device, or even off a generator, only use 1/8 or so, 1/7, 1/8 is a huge savings. That's that much less fuel to haul, or that much more energy you can use for something else, some other type of appliance. So what I try to get people to think about is, what are the conditions nearby to their cabin or their fish camp or mining camp? And I have them think about, how windy is it, and what times during the day and what times during the year, or at the site wherever they're working or doing their thing off grid, or how fast is a stream or river moving nearby. Okay, by fast I mean the constant flow. So there are some areas where you've got rivers and creeks that also you know, have maybe little flow. There's not a lot of water coming down, but it's very concentrated, like drop-off streams in southeast and stuff like that. You're going to use a different device for capturing that type of velocity off of a small flow, as opposed to the Yukon or the Tanana River, where you have a very wide area with a lot of flow, but it's very slow. So we use a couple different devices that I'll show here in a minute. But also then, for those who are looking into solar, either passive, where you just have a box that collects heat and plows it into the ground or into your greenhouse or into your house as the sun is there, or whether you actually have direct solar where you're collecting the energy in battery form or making it into electricity and using it right off the panel. I have them think about, is there direct sunlight nearby? And do you have a wide, spacious field that's going to allow, during the seasons of the fall when you go hunting, if that's when you use it, for a lower sun not to be blocked out by the trees? And then I also get people to start to think about, is there some type of hot spring nearby? Some type of hot spring. Because really, you can get thermal energy. You can get thermal energy out of the river without having to have a generation device. So when I go and it's 20 below and it's in the middle of February to Chena Hot Springs, I see huge pockets where there's steam rising and where there's no ice. In other places, the ice is as thick as a foot in some places. And so it's possible that on that low-grade heat, if you can capture the hot water with a pump or such like that, you might be able to convert it into some electricity, or you might be able to just collect it and use it for preheating frozen foods and such in Ziplocs, or possibly water bottle or water mattresses, in the bed, things like that. So just kind of a radiant heat. So I get people to think about where you're going to go, think about what the area is like, because whenever you set up some type of renewable energy device, you're going to need to have a certain type of stability around to keep your device in place. And you want it to be the right place. You don't want to, if you're up on the north side of a mountain, necessarily go for solar because you got a good deal on it, or your grandpa had it and you thought it was cool. On the north side, that might be a place for wind instead, or if there's a creek, obviously hydro. So anyway, there are different devices. Also, when you take hydro off, unless you actually have a small dam with a turbine, which is one type of hydro, going in, damming it up, and having a head so that water falls over and spins a turbine. If you don't have that kind of setup, and most people don't for their own personal use, then you're going to end up in a situation where you have to probably store what type of energy you're going to get off of a much smaller scale. So the devices I'm going to show you, for instance, you couldn't just on demand probably to do your whole cabin how you want to do, depending on how luxurious you make it. You won't be able to just go ahead and kind of flick the switch and have everything operate all at once. The devices I'm showing you gather energy, but you're going to probably end up trying to capture it and plowing it onto batteries of some kind. And so the best type of batteries out there right now for hydro devices, or actually solar and wind, are deep cycle batteries, and this one is a lead-plated one, but they have come out with AGM, glass mat batteries, that can take the load and store it, and they're only about 30% more money now than these lead-based ones. And the nice thing is there's no maintenance on the AGM or the glass mat, and they're sealed. And they tend to do better performance, at least in cold areas from what I've seen. So you're going to end up having a type of water device, a hydro device, that's going to take energy, it's going to spin in such a way that it's going to run magnets and copper and make electrons, and then you're going to port it onto batteries. But in general, no matter whether it's a solar panel or whether it's a small hydro propeller, always be sure that when you get your batteries lined up, and you can put them in parallel and make a bank, okay? Or in some case, and you want to talk to a battery expert, they may ask you to do them in series depending on the application you have. But in between the device in the upper right, left-hand corner and the actual batteries, you want a charge controller, because those batteries aren't cheap. They're about $250 a pop. And so you want to get as much as many electrons on there and cram them on there very efficiently, because how they go on the battery from your hydro device will determine their livelihood, how long they'll last and take a charge and a full charge. So the other thing that I go over with people is that if they're then going to go ahead and come off of their batteries and use it in a normal 110 type of plug device, like what you have in the wall, you want to get a pure sine or a true sine inverter. I can go and get a modified wave inverter for $50 for 750 kilowatts that'll run my toil stove. Over time, it'll also degrade that motherboard. And so if you're using things that have kind of a digital board, be sure that when you take off of these batteries that you get a pure or true sine type of inverter that takes the 12 volt and it transforms it into 110. Now, let's take a look at the two, probably the two most popular hydro for Alaska users, and that is on the very bottom here. Do you see a slide that says power production considerations?
No, we're still on that first slide, the practical Alaskan grown remote energy solutions. The slide hasn't changed.
Okay, how about now?
Yeah.
Power production considerations, we're on that slide now.
Okay, I'm sorry. So let me just back up here for a minute. So I was talking about batteries. So here's a battery, a deep cycle battery like for a boat that's 12 volt, and those are about 250 a pop. And again, the AGM, the ones that are sealed, are going to be about 30% more, but they really are worth it. And so you can get several of them, and down here in the lower left-hand corner, you can kind of tie them together. And then with your device here, I have a solar panel in the upper left. You see where this is on the slide that says DC charge, right?
Yep. Yeah, we're there.
Okay, that's where your actual turbine is going to be, your water turbine. Okay, and so what I was saying is that little box in the middle of the wire that goes from the one to the other charge controller, spend the money to get a good charge controller to make your batteries last.
Mm-hmm.
And so then I was saying that when you take energy off of the battery, you've got this inverter that will convert the 12 volt into, basically any 110 appliance, whether it be a
We lost
charger.
sound.
So now, power production considerations. On the bottom left-hand corner, do you see kind of a gray vertical wheel with a little red valve on the edge of the picture?
I guess that's what it is, though. It looks almost like an old-fashioned radio.
Yep, it does. And what that is that's called a Pelton Wheel. And it's just as old-fashioned as you can get in technology, but it works. What you have is you have a plastic housing that's protecting a wheel where that little silver or that little nickel nut is in the middle, that bolt. And on that wheel are probably about 30 little spoons. And all this thing does is you can't see it on the left side of that housing, but you have a 1.5 inch plastic inlet that you can taper larger pipe, 4 inch to 3 inch to 2 inch, and really get water whipping through as you constrict the water. Maybe you actually set this in a stream, and maybe you point the pipe so that it runs up a waterfall or even up a meandering creek. And as the water comes through that tube and it restricts, it brings the water in and it shoots it into this housing, and it will whiz that little wheel around with those spoons catching the water, and then they just dump it and it just drops out the bottom. And what ends up happening is you've got wire and magnets on the other side. It's making electrons, and then you have a cable coming off it, and you can hook it up to a 12-volt battery. Now, that works well where there's no debris, where you have a high velocity and you have a low flow. You don't have a lot of volume coming through. However, if you're on a flat river, then you want to go ahead and go with this propeller type of wheel. These run about $1,500, And this just simply anchors down on the ground of the river, and you just let it bob up above. I don't know if that's styrofoam or what you buy particular buoys, and you just let that propeller whiz around. And you've got a cable about the size of a nickel coming out of it, and you're plowing it onto a battery bank. Now, the advantage of using these at camp as hydro sources is that it doesn't matter whether it's sunny or not. It doesn't matter whether the wind's blowing or not. The streams and the rivers always flow. Now, albeit during winter, some streams stay open, and so you can use a Pelton Wheel. You may need to do some breaking of ice depending on how voracious the creek is, or the stream. I said river, but I meant stream or creek. Now, in a flat river, obviously you're going to have difficulty with ice forming, but as I understand, they also use these propeller styles under the ice, okay, where you have a low flow, so over time it gets thicker, but this thing stays down. You set it, from what I understand, so that it can still capture the power. Obviously, you need to be careful of the board getting torn up during breakup and such as that. There's another device that's usually used at hydro plants called a Francis wheel. And it's like the Pelton wheel, only it's turned over on its side. It's a Pelton wheel on its side. And while I was in Iceland, I saw a massive, massive underground plant where they had 3 of these sticking up. And what they would do is they would have a head at a dam, and they would have the water fall about 30 feet or such into big pipes, and the velocity from the pipes would then curve, and this was underground, so it was below where the water even hit the bottom of the dam, right? And it would just shoot it by these horizontal wheels, and it created immense amounts of electricity that they had an electrical grid, and they could dump it straight onto their electrical transmission lines. So, you know, these may seem like old-fashioned methods, but they work. Any questions at all on that? Now in Southeast, it looks like I got a couple minutes left here. In Southeast Alaska, they've had kind of a situation where they had really cheap power for a long time at around 6 cents a kilowatt hour, I believe, 7 cents, because the water was free and it would always flow. Valdez has a large dam, and it lets the water come down the Solomon Gulch, and they're at 22 cents a kilowatt hour. And there's a real sizing that you need to do so that you have power for all your needs, or you end up buying a lot of battery capacity, which is expensive. And so it can vary. Like I say, in Southeast, what happened was power was so cheap that people started to use electric heat instead of other sources. And then in general, they needed to add on more diesel generators because it takes a long time to build a large dam. But for personal use, you're not going to fall into that difficulty. And one of the places that I would suggest before I think this may cut us off here at 10 after, possibly 15 after. One of the places, and it's not the only place, but it's a pretty good outfit that you can go click on and actually look at the different turbines and then the different type of charge controllers and batteries, is ABS Alaska. Capital B, capital S, Alaska. Now, I'm not promoting them as a vendor, but I'm saying that if you go to their website, they're both in Anchorage and Fairbanks, they have a pretty nifty way of showing their devices. And it might be a place to start to look at some hydro. I'm sorry if that wasn't all that it was cracked up to be. I just kind of skimmed that off my remote energy. I do have a full hydro presentation that was done with some work out of the western states on how hydro is used for irrigation in the western ranching states, as well as how hydro is used on a much more large utility basis. And I don't have my list of classes coming up for the next couple Tuesdays, or actually I think we just have 2 more Tuesdays, I believe. I don't know if it's on there or not, but you could always email me at alnashjr@alaska.edu, and I could certainly drum up that PowerPoint and send it to you if you were interested. Any other questions at all on hydro?
No, that was great. Thank you so much for adding that on.
Yeah, I mean, that will probably give you at least a place where you can start to look. Now, since we've got a little more time and I realize this might cut off, I'll show you the ultimate of ultimates. And that is where the problem with solar and the problem with wind is you have varying wind, right? And with solar, half the time during the day it's not, well, depending on where you're at in Alaska, what season, but it's not always shining, right? And you do have cloudiness. And water is good, but water, you know, can, those water, depending on how much you need on your battery bank to pull off and then recharge your battery bank, you know, you may not have good access to a place on the river where there's not debris always banging around your turbine. And so it might be down for a while and you have to go fix it. Or you may not have a situation in the creeks or the streams where you necessarily are able to have year-round water. So this is a device, and if you'll go to our extension YouTube site, and type in Dane Ilana, D-A-Y-N-E Ilana, you'll see a 20-minute video of us interviewing Dane about this particular device that he created. Do you see back on there that power production consideration slide?
No, all is you now.
Okay, let me see if I can put it back on. No, let me try one more thing here. Because Dane Ilana has put together a cart that can be pulled by snow machine or four-wheeler with a 2-inch, or a pickup with a 2-inch ball hitch. And it has on it a mast that was once used. Okay, here we go. Let's try this. It has a mast on it that was once used for a light for a construction company that he put a turbine on. And then on top of that, he put a, let's get back to this presentation. There you can see the power production considerations.
Yes.
Okay, so let me get through here. On top of that, he ended up putting a solar panels on the sides of this cart, okay, as well as then a little wire coming off of the cart to throw a turbine in the water. So he can pull that up to a river. He can have this spin when it'll spin. He has panels here that will collect it. The water is contributing, and he has a battery bank inside this cart. This is a Whacker cart. Whacker is the company that makes a lot of construction carts. He can take these wheels off and he can put skis on it. He figures he has a week's worth of labor making the thing if he gets the cart with the generator, diesel generator already pulled out of it. And it takes him about a week to put it together and under $1,000. He clamps it on and he goes. So he sets it up, and if the water is really flowing, fine. If it's not, that's okay, because you got wind and solar, all three devices dumping at the same time, where your charge controller and your inverter are with the batteries in here.
Wow.
So like I say, if you go to the extension, UAF Cooperative Extension website, and you put in YouTube Dane, D-A-Y-N-E, Ilana, E-L-L-A-N-N-A, energy cart, it should come up for you, and you can always contact me if not, and I can send you the link. It's a good 20-minute video to see how he made it. Any other questions at all, or?
Nope.
Okay, great. Well, let me just ask, total in Haynes, did we have about 4 folks?
Yeah, 4 people.
And how about in Homer, was it about 5?
4.
4.
Okay, and none in Seward?
Looks like not.
Okay, that sounds good. So we have 2 more of these next Thursday, or excuse me, next Tuesday at noon, and then the Tuesday afterwards. And you can take a look at the list and see what will be up next. So thank you for coming.
Thank you.
Thank you very much, Art.
Thank you.
And you can always contact me on any other energy questions. Part of my job is technical assistance as well as workshops. So.